Hey you, come this way.
To do the peg game!
To start off, we want to give you guys some rules to the peg game. The rules are as follows. In order to begin the game, you take one peg, move it over another, and remove the peg that it jumped over. You continue to do that multiple times. The goal of the game is to get down to one peg at the end. By doing that, you would have won the game. This right here is what we call the original graph. This is how the game starts. Each peg hole is a different number. So this one right here is 1, this goes 2 and 3, 4, 5, 6, 7, 8, 9, 10, and 11 through 15 as followed.
We also created a way to annotate different moves that you could make. For example, if you wanted to move the 6 peg over the 3 peg into the 1 spot, you would write it 6, jump 3, go 1, and that would get rid of the number 3 peg. Another example of a move that I could make is from going from the 4th peg to the 6th peg by jumping over the 5th one, written 4, jump 5, go 6. The next move you can make is going from the 1 peg to the 4 peg by jumping over the 2 peg, written 1, jump 2, go 4.
The reason we came up with this annotation is because we wanted to keep track of the moves we were doing in order to further our exploration. By doing this, we were able to keep track of our moves and be able to go backwards from our moves. One of the first properties that we came up with was called the Jensen property. Here is an example of the Jensen property. This is the original graph that we have where we have a peg at 7, 8, 9, and 14. And we wanted to flip it on the other side where this would be the line of symmetry. So on this side, we flipped it and we had 10, 9, 8, and 11. So as you can see, the 7 and 8. So the other part of the Jensen property is being able to rotate the graphs. So we kind of showed that through a couple triangles here. So if this was the original graph, we took that and we rotated it this way. And we now have 9 and 14 being filled in by 7 and 8, and then 8 and 7 being filled in by 5 and 3. Which you can also see if you were to take the peg game and rotate it yourself, you could see the different graphs that could come about it.
Every project, we also defined something called a Dimick product. Now this graph right here is actually a Dimick product of a graph. The way we can know if it's a Dimick product is if we can move backwards from this graph to another graph. So if we move this peg like this and almost retrace our steps, we know that the original graph that I showed you was the Dimick product of this one. And we can even make another Dimick show another Dimick product of this graph.
Another phenomenon that we've defined is called the sand circuit. Now, the sand circuit is a graph that can be completed with just one peg that's called the operator. To complete the graph, you go from here, there, there, to there, leaving just the operator and completing the graph. A majority of our inquiring about the peg game had to do with the sand circuit. We figured out that this right here is the largest sand circuit that is possible. It's solvable with the operator. Another term that we defined in order to help us dive deeper into exploration was subgraph. An example of a subgraph is, say that this is the original graph, this would be a subgraph of it because it is part of the original graph but not the whole. An interesting aspect about the largest sand circuit is that every other sand circuit also lies within it. For example, the line that I showed earlier is a subgraph of the largest sand circuit. We found that every sand circuit is a subgraph of the largest sand circuit, except for a few exceptions which have pegs in some of these holes, but those resemble the same features as subsets of the largest sand circuit. They're just simply shifted. For example, this triangle, that triangle, using the operator there. But yeah.
After discovering the sand circuit, we had to ask a lot of questions about what the sand circuit actually meant. We looked at to see if the largest sand circuit that we found was actually the largest sand circuit, what this meant and why it was the largest sand circuit, and how we could produce the largest sand circuit for bigger base triangles. We also looked in to see if every sand circuit was a subgraph of the largest sand circuit, and if that was actually true. And lastly, we wanted to see if a sand circuit was even possible, whether it was a Dimick product of the original graph or not.
When trying to figure out if this graph is the largest sand circuit, and if it is, why would it be the largest sand circuit, we noticed some interesting qualities about it. We noticed that every odd row, for example, the first row, the third row, and the fifth row, the first one doesn't have any pegs in it. The third one has one, and the fifth has two, each skipping the first one and alternating, while every even row fills the whole row. These are the characteristics that make up what we think could be the largest sand circuit. To make sure that it is the largest sand circuit in other bases, we took this pattern and expanded it into a base of triangle 9.
So following the pattern of having full rows every even row, and then every other peg placed every other hole on every odd row, we decided to make the sand circuit larger to see if it was solvable as a sand circuit, the larger base we made, and to see also if this is probably the largest sand circuit we could make in it. This is actually an example of a sand circuit in base 9, and it is solvable. We have done it. Other than that, we hypothesize or think that this is the largest sand circuit that can fit into it because of the limited moves that each peg has.
Another thing that we started to look into was dead graphs, and what a dead graph is basically when you can no longer move any of the pegs on the board. In other words, you lose the game. As we think that we had found 2 large dead graphs which are of size 6. So there are 6 pegs that are left, and none of them are able to move. This is the first one that we discovered, and this is also a Dimick product of the original graph. So you can get to this product from the original game. Another example of the largest dead graph that we think we had found is if we move the 1 to 13. And we also think that this one is one of our biggest dead graphs that we were able to find.
One of the more interesting things that we found after exploring dead graphs and sand circuit is that each peg's movement is limited. All of these pegs can only go to the holes that are filled because you have to hop a peg in order to get into the new holes. Because of this, we found that the game is a lot more limited in the number of moves that are possible. After discovering this, we now think that the largest sand circuit that we have shown is the largest sand circuit, because if these are the only holes that this peg could move into, then this is the only place where the holes can be open to have the most opportunity for the game. For further exploration past the project, things that we would look at is proving the fact that we have discovered the largest sand circuit, proving that the largest dead graph that you can produce from the original graph is 6 pegs, especially exploring the finite moves that each peg has. Because of this, we think that there are a lot of weird things about this peg game that we haven't even discovered yet. One of the things that we could never find and that we don't believe you can find is that there is no sand circuit that is a Dimick product of the original graph. Because of this, we think that sand circuits are kind of a mystery and even more interesting to find.